now come to the main theorem about Baire spaces, which is the Baire Category Theorem. So what is the Baire Category Theorem? So theorem Baire Category Theorem, it states that if a topological space X is compact Hausdorff, if it is compact Hausdorff or a complete metric space, then X is a Baire space. So it gives a wide variety of examples of Baire spaces, namely those spaces that are compact Hausdorff or those that are complete metric spaces. So now we have already seen what are compact Hausdorff spaces, but we haven't seen what are complete metric spaces yet, and we will define the notion of a complete metric space, and then we will prove the Baire Category Theorem for both compact Hausdorff spaces as well as complete metric spaces. Now remark on the terminology about this term category. So remark the term category, was used by R. Baire, the mathematician after which Baire spaces are named, and he used the term category to define two kinds of spaces. So he defined two kinds of spaces, those that were of first category. So a subset A of a topological space X is said to be of the first category if it is contained in the countable union of a countable collection of closed sets with empty interiors. So this means that A is of the first category implies, if and only if actually there exists a collection Bn, each Bn is closed and interior of Bn is empty for all n in the naturals, and such that A is contained inside the union of all these Bn's. So in this case the set A was said to be of first category, and space was said to be of second category simply those spaces that are not of the first category. So a subset A is of the second category if it is not of the first category. So this is just the complement of the collection of first category spaces, and with these terminologies we have the equivalence. So this can be stated as a theorem. States that X is a Baire space if and only if every non-empty open subset U of X is of the second category. So remember that we had the closed set definition of Baire spaces, which said that space is Baire if and only if it satisfies that every countable union of closed sets with empty interior must have empty interior. Therefore, if a non-empty open set is of the first category, then the space cannot be Baire, and vice versa. So I leave this as an exercise for you to write out the proof of this theorem carefully, just by using the definition of Baire space, a first category space and a second category space. Okay, so this was just some remarks about the term Baire Category Theorem. However, we will not use these terms first category and second category, and we will only use the term Baire spaces. And now to prove the Baire Category Theorem, we need some separation lemma. So separation lemma for compact Hausdorff spaces and metric spaces. So what is the separation lemma? So lemma 3.2. So it states that so this lemma states that if X is a compact Hausdorff space or a metric space, then it satisfies the following condition, satisfies the following property. So the property says that if you have a closed subset A in this space X, so A is closed, and you have a point X which does not belong to this closed set, then there exist open sets U containing X and V containing A, such that U and V are disjoint. So this is a kind of generalization of the Hausdorff property. So in the Hausdorff property you had two distinct points X and Y, and you had disjoint open sets U and V which contained each of these points, and they are disjoint. So this is the Hausdorff property, and in this lemma we have one of the objects is still a point, but the other object is now a closed set. So let me draw a picture here. So let X be a point and A be a closed set. So let's say this is A, and now you can find open sets U containing A and V containing A, which are disjoint from each other. So this is the separation property in the separation lemma. So let us prove this statement, the separation property, both for compact Hausdorff spaces and for metric spaces. We will prove this one by one. So first, proof for compact Hausdorff spaces. So the arguments will be a little bit different. So we do this one by one. So first, for compact Hausdorff space, so for each point A in A, so since x does not belong to A, so x is not equal to A, then this implies by the Hausdorff property, so by the Hausdorff property, that there exist open sets which I denote UA containing X and VA containing the point A, such that UA and VA are disjoint. And now we use the fact that A is closed in a compact Hausdorff space. So A closed in X, which is compact Hausdorff. This implies that A is compact because closed subsets of compact spaces are compact. So A is compact, and now this collection VA is an open cover of A, and this implies that there is a finite subcover VAI, I from 1 to n is a finite subcover of A, of not A, small a, but capital A, the closed set capital A. And now what we are going to do, so we are going to take the union of these finitely many open sets VAI, but the corresponding sets, for the corresponding sets UAI, we will take the intersection. So define U to be the intersection of the sets UAI I equal to 1 to n, and V to be the union I equal to 1 to n of the sets VAI. And this kind of argument we have already seen once before. So you have this space X, this point X, and you have some closed set A, and for each point A you are considering an open set. So for each A you have an open set. So these are the VAs, and there are finitely many of them which cover the set A. And now you have the corresponding UAIs. So UAIs can be of something like this, UAIs, and these are the VAIs. And now you are going to take the intersection of all these UAIs and the union of all these VAIs. So what I claim is that the intersection of U and V is the empty set. So let's prove this claim. So if X belongs to U, so suppose that X belongs to U intersection V. So since X belongs to V, this means that there exists some I in this set 1 to up to n, such that X belongs to VAI. And this also means that since X belongs to U, this means that X belongs to UAI, but UAI intersection VAI is empty, which is a contradiction. So by our choice of the UAI and the VAI, they are mutually disjoint, so this leads to a contradiction, and this means that the intersection is empty. And so now we have the sets U and V. So this means that there exist sets, open sets open sets U and V in X such that X is contained in U, A is contained in V because it was a finite subcover. This was the union of the VAIs, this is which was a finite subcover, so A is contained inside V, and the third part is that U intersection V is empty. So this proves the lemma for compact Hausdorff spaces. And as a corollary, we have the following important lemma which we will use in the proof of the Baire Category Theorem for compact Hausdorff spaces, which is that if X is compact Hausdorff and A is a closed set in X, and X belongs to an open set, and X is not in A. So the X is contained inside an open set U, but X is outside this closed set A. Then there exists a neighborhood U1 of X such that X belongs to U1, of course, and this is a subset of U1 closure, but U1 closure is contained inside U, and U1 closure intersection A is empty. So here we have a minor modification of the previous configuration where you had a point X and a closed set A, but here they set the point X is already contained in some open set U which may or may not intersect A. So something like this. So this is U, and now we have to find a neighborhood of X. This is U1, which whose closure is contained inside U and does not intersect A. So how do we show this using the separation lemma that we just proved? So to prove this, let us take in the separation lemma the point X inside U and the closed set A, and this means that there exists neighborhoods V and W. X is contained in V, W contains A, so these are open sets V and W. V is containing X and W is containing A, and V and W are disjoint. And now this gives you a neighborhood of X. This is V is a neighborhood of X such that V closure intersection A is empty. So I claim that this automatically implies that the closure of V with A is empty. So this is because, so if some point Y belongs to this intersection, then the neighborhood W, then W is a neighborhood of Y which does not intersect V, which means that Y does not belong to the closure of V, a contradiction, and this means that V closure intersection A is is empty. And so one of the neighborhoods that we want is from V, but now our V is not guaranteed such that the closure of V lies in U. So to ensure that the closure of V is inside the open set U, we apply the lemma one more time. So apply the separation lemma one more time to this time to the point X. Okay, so X is in U, and the closed set B, which is the complement of U. So now this means that there exists open neighborhoods V1 of X and W1 of B such that, so here B is contained inside W1. This is what I mean by an open neighborhood of the set B, such that the intersection of V1 and W1 is empty. And now we can take the intersection of V1 and the set V, and this will be our required open set. So let U1 be the intersection of V and V1. No closure. Now claim is that X of course belongs to U1, and this is a subset of U1 closure, and the main part is that U1 closure lies inside the set U. Okay, so why is this true? This is because if X belongs to let's say if Y belongs to U1 closure, so this implies that Y belongs to V intersection V1 closure, and this is a subset of V closure intersection V1 closure. And note that we can again apply the part we have already shown, which is that the closure of V and A is empty. So this means that Y cannot be in A, and also that Y cannot be in B, which was the complement of U. So the same argument that we used to show that V closure intersection A is empty also applies here for the second application of the separation lemma, and we have here that V1 closure intersection the closed set B is empty. So here since Y belongs to V closure, then Y cannot intersect A, and since Y belongs to V1 closure, it cannot intersect B. So this means that Y belongs to U, and therefore the set U1 closure is a subset of U, and U1 closure intersection A is empty. So this is how we have proved the separation lemma, and the corollary that we have stated here, we will use it in the proof of the Baire Category Theorem for compact Hausdorff spaces. And now we come to the proof of the Baire Category Theorem for compact Hausdorff spaces, and we will use the separation lemma and the corollary that we have just proved to prove this theorem. So note that X is a Baire space if and only if the definition says that we have a countable collection of closed sets with empty interior, and this implies that the union must have empty interior. And this is equivalent to saying that given any open set U0 in X, there exists a point in U0 which does not belong to any of the closed sets AN. So this is the condition that we will use, the last condition that I've written here, and this is what we will use to prove that prove the Baire category theorem. So we have to show that given any open set U0, there exists a point in this set such that it does not belong to any of the open sets AN. Now the first step in the proof is to use the corollary that we proved above, and so given an open set U0, first of all we know that there exists a point Y in U0 says that Y does not belong to the first set in the collection of closed set, which is A1, and this is because the interior of A1 is empty. So interior of each AN is empty, and in particular for A1 as well. And so this means that U0 cannot be so of course this is a non-empty open set. I've assumed U0 to be non-empty, and so you have a point Y in U0 which is outside of A1, otherwise all of U0 will be contained in A1, and which will violate the condition for the interior of A1 to be empty. So then we have chosen this point to Y1, and now using the corollary above, we find open neighborhoods U1 of Y such that not neighborhoods but just one neighborhood, an open neighborhood U1 of Y such that U1 closure intersection A1 is empty, and U1 closure is a subset of the open set U0. So this was the corollary that we proved above. And for the second step, we have a kind of recursion. Construction. This is the recursion step, where we assume that for n greater than 1, the sets U1, U2 up to UN minus 1 have been defined, and all of them satisfy UK closure intersection AK is empty, and UK closure is contained inside UK minus 1 for all k greater than 1, greater than or equal to 1 in fact. So this is we suppose that we have chosen all this, and now we will construct UN such that UN closure intersection AN is empty, and UN closure lies inside UN minus 1. So what we are doing is constructing smaller and smaller open sets whose closure lie in the open set in the previous step, and such that they are disjoint from the closed sets, the given closed sets AN. So how do we construct UN given all these sets up to UN minus 1? So since UN minus 1 is non-empty, and we have that there exists a point Yn which belongs to UN minus 1, but Yn does not belong to An, and this is again because the interior of An is empty. So we have this point Yn, And now apply the corollary above to this point and the set yn. Apply the corollary to the point yn and the closed set an, and this gives you that there exists a neighborhood un of yn such that un closure intersection an is empty and un closure lies inside un minus 1. So this is a repeated application of the corollary that we have proved before, and this is the recursion step. So given un minus 1, we are constructing un, and we are basically having a sequence of neighborhoods. We get a nested sequence of neighborhoods of open sets, let's say, of open sets un for each n, such that you have u0 which is containing u1 closure. u1 closure contains u1, then this contains u2 closure, u2 closure contains u2, and so on. And at the nth step you have un minus 1 closure which contains un minus 1, and this contains un, and this chain of nested sequences goes on and on. And we will only consider the closures of these sets. So this one should be un closure, and here there is a un. So we will only consider the closed sets u1 ui closures. So consider, so this is the third step, in fact, step 3. So we consider the collection of closed sets uk closure k in n, and note that this collection satisfies the finite intersection property. This is the finite intersection property. It just says that given any finite subcollection, say uki closure I from 1 to, let's say, capital N, then the intersection of all these sets uki closure, this is non-empty. And this is simply by taking ki to be the smallest of all these smallest integer or smallest natural number among the set k1 k2 up to kn, then we have that uki closure is a subset of all the rest of them. So ukl closure for all L in the set 1 to up to n. So this means that the intersection will be precisely the set uki closure, which is non-empty by construction. So therefore we have the finite intersection property, and this means by the compactness of X that the intersection of all these sets uk closure, this is non-empty. This is the finite intersection characterization of compactness that we have seen before. And so if X belongs to this intersection, then I claim that X does not belong to, first of all, that X belongs to u0 and X does not belong to k for all k in n. So this is just because, this is simply because x belongs to let's say u1 closure. This is a subset of u0, first of all, that x belongs to u0, and secondly, since x belongs to uk closure, this means that x cannot belong to ak, as we have uk closure intersection ak was empty by construction. So therefore we have these two properties that we wanted. We have found a point in the open set u0 such that this point does not belong to any of the closed sets in our collection of closed sets with empty interior, and this proves that X is a Baire space.